actually started in 1926 before Crosley owned it, and WSAI built their 5 kilowatt station out here. The station was built in this building that's now a home for the chief engineer, with apartments upstairs so that the engineer lived there and could be on site all the time. Later, the house was renovated into more apartments when WLW had taken over. So WSAI moved out, I think around 1935. They moved down into the hill area just above downtown Cincinnati, the site where the WLW television tower is now. The flat top antenna, the base of the flat top was out here behind the garage, went over the top of the house, and another flat top in the backyard, and a vertical radiator that came right out of the side of the house and went straight up. So when Powell bought the station, he of course was ready to go to 50 kilowatts, and he built the front half of this building. We have construction photos of the building being put together. The WLW antenna, the original WLW antenna, was another flat top with one tower out there where that clump of trees is, and at the back end of the property. The white building that you see, the white wooden building, was the tuning house for the WLW flat top. An interesting story that Geoff and I were able to confirm is that the rumor was always that that building was built out of the packing crates from the Western Electric 7A transmitter. We proved that it was, right?
When you go in that building and you look up in the rafters there, you'll see some Western Electric logos.
the black ink stencil logos from the shipping crates,
Yeah.
they're there.
It's like the,
So when the preparation for the 500 began, they wanted the vertical radiator, and that's when they went out into what was a cornfield and put the Blaw-Knox in. The Blaw-Knox sits on a base that goes 70 feet into the earth. There's 150 tons of steel in the tower, and the full pressure on the base insulator is 470 tons. Okay, because of the extra weight from the guy wires and the tension on the guy wires.
27,000 pounds times 8 guy wires.
Okay,
Standing rigging.
so how high is that now?
the tower is, I believe, 757 feet today. It was 830. They didn't take the top off the tower structure. They took the flagpole off the top of the tower. The 500 kilowatt transmitter as well as the 50 kilowatt transmitter were both water cooled. The 50 kilowatt, they could dissipate the heat with an indoor heat exchanger with blowing air through it and exhausting it outside. 500 kilowatts, they couldn't. So they built the spray pond out here, and they had 2 water systems. They had a deionized, or not deionized, but distilled water.
Yeah.
Deionized distilled water closed circuit to a heat exchanger, and then just pond water. And they cooled the water by spraying it up in the air and letting it come back down and collect in the pond. The pond is about 4.5, 5 feet deep. There were 4 of these rotating nozzles, 4 nozzles per turnstile, and the way the nozzles were aimed, it caused the nozzles, the spray thing to rotate and spew the water out. Okay.
Better evaporation.
So Geoff and I had the honor of taking an 80-plus-year-old lady who grew up on this property when she was a teenager. She lived in the house. Her dad was the director of engineering for a brief period of time, Joe Whitehouse. And she told us the stories about going to Mason schools, town of Mason right over here. And she was the only girl in school that had a swimming pool in her yard. And it was a heated
Nice
swimming pool.
Yeah, for the heat exchanger.
She also told stories about walking with her friends 1 foot over the other on a transmission line all the way from the transmitter building down to the tower base. And she had some other very interesting stories. No. Okay, we're going to go inside. You're going to see a lot of transmitters, but let me caution you, this is an on-air site, okay? So don't touch buttons, don't open doors, don't poke at any of the gear that is keeping them on the air, because I can guarantee you this will be the last trip that ever gets taken here if we knock them off the air.
Yeah,
Okay?
yeah. Don't open any doors. The interlocking will shut it down, right?
Don't wander off. Stay close so we can continue our dialogue. I'm going to cover a little bit about the 50 kilowatt, and Geoff's going to take over and tell you all about the 500. Okay? So let's go inside.
The big one. Blaw-Knox. Back up.
The other tower is the backup tower.
Block here.
Yeah.
If I can get you to kind of, hey Ted, kind of, if you would congregate over here in front of the Western. So this part of the building, back to where you see that concrete block wall, was the original WLW transmitter building, built in 1928. When it was originally built, the stairwell wasn't here. There was the Western Electric transmitter, which was installed, and it went all the way basically to the wall. The Western Electric transmitter, the 7A, was one of the first 50 kilowatt transmitters delivered by Western Electric. It remained in operation continuously from 1928 to roughly 58, 59. However, it still remained in operation until after the turn of the last century. Okay? In 1955, Ronald J. Rockwell, who was then the VP of Engineering for Crosley Broadcasting, who was a very prolific inventor, had developed a new way to modulate a transmitter with high-level modulation with no iron in the modulation path. The system was known as the Cap Modulation System. He held the patents on it. It was a very high fidelity system capable of modulating out to more than 100 kilohertz. Okay, very wide band, no iron, very low distortion. So in order to build that idea into a real transmitter. He built a prototype, low-power transmitter, and then went about designing and building the cathinode transmitter. In order to do that, they modified the Western Electric, updated it with newer tubes. The Western Electric was a low-level modulated transmitter, and the amplifiers were linear amplifiers. Converted it to Class C, built a Class B modulator, and power supply and modulator were put in the basement under the transmitter, and then proceeded to build the cathinode transmitter. They did all this with only signing off for brief periods of time overnight, staying in operation because they only had one transmitter. The cathinode came up, it was 4 cabinets, not the 3 you see there, and it became the primary transmitter for a period of time beginning in 1958 to sometime in the late 1960s. The cathinode was Rockwell's baby. It was, because it was DC coupled through most of the stages, it was very finicky about bias and balance. And Rockwell was the guy that could make it play, and when he retired in '65, many of the engineers had trouble making it play. So they eventually converted it to a Class C, Class B modulated transmitter, duplicating the modulator and putting it in the basement, and by doing that they were able to cut down to 3 rack cabinets. In 1976, Avco wanted out of the broadcast business. They wanted to sell the place, but they figured they would have trouble selling it with a 1928 vintage transmitter and a homemade transmitter. So Clyde Hanley went out and bought a 317C from Continental and installed it, and when they did that, they put up the concrete block wall, which separates us from the addition to the building that houses the 500. So originally this was open all the way to the 500. That's how I remember it as a kid. There used to be a control room over here where they wrote audio levels, and there were 2 shortwave transmitters, WLWO and WLWK, that were back in the area where the 3DX50 is and the Continental is located. The stairwell got moved, and there was a control console, not the one that's there. It faced the 500, and there's a lot of pictures of that control console, which was a wooden cabinet, not the metal cabinet that we have today. Then in the mid-90s, they went to solid state with a Harris DX50, and in the early 2000s, we were developing the 3DX50 at Harris, which was now located in Mason, Ohio, instead of Quincy, Illinois, for the R&D labs. So we picked this as the development site, the test site. So the original 3DX was the test model, was built and brought over here and tested, debugged, and so forth, and then we ended up trading that transmitter out when we actually put it in production. So, any questions real quick about the Western?
So Jay, if they weren't doing regular plate modulation, there's a big modulation transformer downstairs, isn't there?
Yeah, but that's for the 500. We'll see that in a bit.
Okay.
There are 2 cubicles for power supplies and plate modulators.
So that wasn't for the original.
For the 50s. The original Western did not have a modulator as we know it today. It was a low-level Heising modulator. Heising was a Bell Lab guy, Western Electric Bell Labs, you know, and the amplifiers were linear amplifiers. Almost all Western Electric transmitters in the day were low-level modulated. They were not high-level modulated. By the way, in 1999, December 31st, they were worried about Y2K. 2 transmitters, microprocessors, do we really want to trust that? So the answer was no, we don't, even though we said we don't have a Y2K problem. So the last time that this transmitter operated was starting at 10 o'clock on the 31st, December 31st, 1999, until about 2 o'clock in the morning.
Wow.
They ran the Western Electric, and they told people we were running on a 1928 transmitter.
Wow.
How did it sound on the air? Did you get a listener's report?
They say it sounded quite good.
Okay.
Now keep in mind, it wasn't the original 28 because
No.
it had been highly modified.
Not the guy, yeah.
Okay. Any other questions about the Western or the Cathano?
Are either one of them operational now?
No. So the only thing keeping the Western from operating is that it has a defective heat exchanger. Okay? The heat exchanger was allowed to freeze up and burst some of the tubes, and because of 3 other transmitters that are operational, they decided not to repair it. The other transmitter has a short in the modulation transformer, and when they get up to a certain level of modulation, it arcs over and shuts it down. So both of these are no longer operational transmitters. This one could be with a simple replacement of the heat exchanger. And it's just a typical like a car radiator, only much larger, with fans blowing air through it. Okay?
Would it cost to replace it?
Say what?
How much would it cost to replace that?
Probably $10,000 or $15,000 at most. I would guess. It's not a monumental project. They'd have to reload it with distilled water, and it's been sitting now for 15, 17 years, non-operational, but they still light it up, show it off. The meters are the original meters. The cabinets got modified a bit and dressed up, but many of the components, like the tank coil and the capacitors and that, are original from the Western Electric.
I gotta take just a minute to tell these people what is on the air. I don't know if you explained it. This box over here is what's on the air. Okay. This is a Harris EX50 kilowatt. It is a digitally modulated transmitter. It's all the same transmitter. It has no plate modulator. It has no EDM pulse duration modulator. It has a stack of modules in it that are turned on and off like a great big analog, digital to analog converter. So there's a stack of modules in here. The audio is digitized. And the digital words turn on and turn off a certain number of modules. So it's directly synthesizing the AM envelope. Okay? The output transistors in this are very unimpressive compared to the LV loss parts you see in an HF amplifier. They are basically MOSFETs like you use in the analog brakes of cars. They're big MOSFET switching transistors that you would see in a switching power supply, or like I said, anti-lock brake system on an automobile.
Silicon carbide or something like that?
No silicon, nothing iconic, just silicon. They're MOSFET. Okay, now somebody asked about filtering it. This transmitter has a band pass filter, not just a low pass, but it has a band pass filter because the sampling rate of this transmitter, when you're turning the modules on and off, is at the carrier frequency. So you have aliasing terms. If you're familiar with digital things, you have a 0 frequency term and you have another frequency term that's plus or minus carrier frequency. So this has a band pass filter in the output. Okay. So that's how the harmonics and the other images or aliasing terms are removed.
And you turn them on and off quick for efficiency and
Yeah. Okay. They're turned off very quick, and there's a lot more to it, but we need to get back to the other end.
So
Yeah.
Let me introduce Ted Ryan.
Ted,
is
okay.
W8SAI,
Oh, wow.
but he is also the chief engineer of WLW Radio, and he is our host tonight. Let's give him a round.
Yay, thank you, thank you. So, what determined to get a Harris transmitter because of location as opposed to not tell as far as the solid state? Oh, that's not because it's so close. Not tell is a lot further away, right?
It's Canada.
Canada, right? Good old DX50.
He's sitting there, what's the 3 things?
I got a 200 gigabyte SD card in here. Oh, look at
I
this.
feel like a snake oil salesman when I get this. So, let's see. Basically, from here down, these are the modulators. So, in each modulator section, there are 4 of these large tubes. Jay was talking about these. They were the 862s, and now they're 892s. Now we'll say a few words about that. Here's one of these tubes. This is the newer 892. They're triodes. So the filament connections are here. This is the grid connection, and the anode or plate is this copper jacket that goes all the way to the floor. That sat in a receptacle there that had water flowing over it to cool it. The original tubes had single-phase filaments. So, as you guys know, maybe from your ham radio experience, typically when you power a filament on a tube, you have to use a center tap transformer so that you can get humbucking out of the system so that the AC filament voltage does not modulate the electron beam in the tube and cause hump. Well, the solution here was DC on the filaments. They had a huge bank of motor generators in the basement. So there were AC motors driving DC generators. What was the current?
So the motor generator sets took 2300 volts AC in. Each motor was 75 horsepower. The generator side was 33 volts at 1500 amps. So it took 4500 amps to light the filaments in the amplifier.
That's total.
Total.
So later, with some technical innovation, this tube has a 3-phase filament. And the filament is wound so that when you put 3-phase AC on it, the modulation of the electron beam is bucked out or canceled out in the construction of the filament. So they were able to do away with the motor generators and go to AC filaments when they went to polyphase AC system, and that's what that tube represents. Anyway, these are the modulator sections. There's 3 of them. When they were working in all combined, they had over 250 kilowatts RMS audio, and you'll see one of the modulation transformers in the basement. They actually the transformers are rated at about 180 kilowatts each. And actually, when we go down there, I'll encourage you to take a close-up picture of the label on the transformer. It's quite interesting. And then down here we had the 8-phase rectifier system. These were originally mercury vapor rectifiers. Well, they were glass mercury vapor rectifiers. Now they went to metal mercury vapor rectifiers. And you can see some of these tubes here. Okay? Anything else?
12 kilovolts and 100 amps.
Yeah. I mean, here's the load amp meter, goes to 150 amps. Okay? And this is the voltmeter, 15 kilovolts. So this was a redundant system. We had multiple modulators, and you'll see in a minute we had multiple RF amplifiers. And So you could lose a modulator or an RF amplifier or both and still keep the system on the air.
Do you have to reduce power?
Yes, of course, you have to reduce power, but you can stay on the air. Now, the other thing I want to mention is, Jay told you earlier, this transmitter bears RCA's name, but RCA Victor Corporation was just really the program management company. The heavy lifting on the audio side was Westinghouse engineers, and on the RF deck side was General Electric engineers. And I did a little bit of research on the engineering team that put this together. And this is basically designed in place. You'll see how the construction goes. This was not built in a factory and tested and brought here and installed. It was built piece by piece here on site. But the team of engineers that built this, I did a little research on them, and I came up with the average age of these engineers was 27 years of age. So you can imagine being a double E, freshly minted double E, 27-year-old guy or gal, and working on a project like this. I mean, they were space cadets in my book.
Did they have women engineers, or was it all men?
They were all men on the team here. Yeah. Hate to say that, but anyway. Okay, so go ahead and take all the pictures you want. So these were push-pull modulators. All of these tubes, both the modulator tubes and the RF tubes, had to be liquid cooled. This is just one piece of Pyrex pipe. Jay can open this up. You can see a huge array. Wait, don't hurt yourself. Yeah. Oh, they're still there. Go ahead and push it all the way up. Yeah, I'll hold it up there. Okay, there you go.
So you can see the piping, the flow meters, the valves.
Yeah, I'll just hold this open. So why did we have the glass pipe? Okay, so the water flowing over the modulator tubes and the PA tubes had to be on a 13,000 volt anode that it was in contact with. That's just DC voltage. Peak voltages were much higher than that. And so it had to be deionized water, completely distilled so that it was not conductive. And so this Pyrex pipe is to provide a long path, pre-peak path, to get the water from high voltage back to ground as it circulated through it without flashing over or causing a loading effect on the transmitter. So there's one of these arrays of Pyrex pipes for every one of the amplifiers. So then when the water came out of these Pyrex pipes and went into the basement, there was a brazed plate heat exchanger. You guys familiar with a brazed plate heat exchanger? It's like copper or bronze material where there are two pipes that are connected, welded to each other, but there's no connection between the liquids in the two sides, but it's a thermal connection. So they would take the heat out of the water that was flowing through this inner loop of distilled deionized water, transfer the heat to the outer loop, which was the pond water, and went out to the spray pond. Did everybody get a chance to come over here and take a look at it? Yeah. Okay, maybe you guys could shift places here a little bit.
Geoff, so the Western Electric is just carrier drive to
No, it was actually
PA and
modulated.
modulator here?
It was modulated. The Western.
There are modulators here also?
Yes. So the drive was modulated as well as the plate voltage was modulated in order to be able to achieve 100% modulation in the transmitter.
Is there a 250 kW of audio, or high-level modulation, did you say?
Yes.
So it's basically 250 kW
It's
of
like
audio.
a Grateful Dead concert.
Yeah, right. Yeah.
So what class of operation are these PAs?
I've done that.
Class C.
Class C,
in the
yeah.
RF amplifier.
Yeah, Class C.
B for the audio modulator.
And those were push-pull.
Yeah, so, it was 180 kilowatts. There were two modulation transformers, 180 kilowatts each. So it was 360 kilowatts of capability, their audio capability.
Say, Jeff, would this transmitter run more than 500 kilowatts?
Yes, we're told, as I get into these amplifiers here, I explain there's 3 amplifiers here. They were nominally rated at 180 kW each, but they could do more than 200 kilowatts. We've heard it, what, up to 700, 750?
They ran, it's documented, when they were in the testing phase, they actually ran it at 800 kilowatts.
800 kW.
Wow.
And
Don't know if they could 100% modulate at
we
that
just
power.
discovered an article from 1934 that Joe Chambers, who was then the director of engineering, wrote, and he said that they had sustained modulation at 400 kilowatts, 400 kilowatts of audio power. Now, unlike modern AM transmitters, the transmitter specs were good from 50 to 10 kilohertz, but the distortion levels were less than 10%.
Yes. Okay, can we close this now? I gotta get across the bridge. Don't get your fingers
Let's
cut.
get somebody else on the other end.
Yeah, okay. All right, don't get your fingers caught. Okay.
Slide her back.
Don't drop it. It's fragile. There you go.
All right. Okay, so. I'll open a couple of these here.
Oh my goodness. The tuning network thing?
Yeah, look at this. Plate tank.
Plate tank.
All right, so you have to peek in here through the glass. So this is one of 3 power amplifiers. They were combined in series. Interesting amplifiers. They had 2. It's a push-pull, parallel push-pull system. So you had 2 of these 892 tubes on this side and 2 on that side. They were in push-pull. What you see behind here, and we'll see when we're going to go around the back of this transmitter. I'm going to show you the tank circuit, but there were fixed air capacitors to resonate the inductor. The inductors are spiral wound pancake inductors. They're not solenoidal inductors. You'll see that when we go around the back. But if you look in there, you'll see things that look like bread racks. That's what they call them. See this tubing, and they're offset. Those are parallel plate air dielectric capacitors.
They're horizontal?
They're horizontal. Look straight back in there. Here across behind those tubes.
Oh yeah.
And they're hand built. I mean, this transmitter is hand built. By the way, there's wood studs in here. This is like a wall that they built, and then the whole thing was sheeted with copper sheeting and soldered to make a box out. Okay?
And built, there's not a duplicate like it.
No. There was another one that was supposedly built for Doc whatever down at yeah.
The border blaster.
The border blaster.
XCRF.
Yeah.
250
And
kW.
I imagine I don't know how much resemblance it had with this one, but they were hand built on site.
Yeah.
And these bread racks were hand built.
Yeah, it was very rarely that they actually ran that much
and you
power.
look at them, they're pieces of tubing that are spaced, and presumably if you got any kind of debris or bugs or anything, they'd fall through. You know? So they were not solid plates, but they were close enough spaced that they had the capacitance to parallel resonate. What you see up here, this inductor here across is just part of the DC feed choke to the tubes. Okay.
I have a question. What did they use to control the frequency? Have crystal or what?
Yes. Crystal was in the Western Electric transmitter driver.
Okay.
And it was ovenized. So they had ovenized crystal oscillators back then.
Okay.
So are you saying that they used 50,000 watts of driver?
Yes.
Now, this is just the amplifier here.
50,000 watts.
This is just the amplifier.
No, I thought there was modulation on that drive. Okay.
Build the modulation and totally modulate it with the flat speed.
Yeah.
Were those tubes used in any other application, or were they custom?
They were used in some other transmitters. You know, some smaller transmitters. These tubes were built, most of them were built by Federal, which was a company that manufactured vacuum tubes. We have all the spec sheets on them too. So, Federal Electric. Okay, so here's the grid current meter. 0 to 10 amps. Grid current. Plate tank circuit. 1 amplifier. 0 to 160. Yeah, this is an RF ammeter, by the way. This is look, it's a nonlinear scale. This is a thermocouple RF ammeter reading the plate tank circulating RF current plate tank circuit up to 160 amps. Okay. Over here you got DC amperes against the grid 0 to 10. You guys have seen some of the controls down there. Those little wheels that look like you're, you know, something from a spaceship or a submarine. Or those were tuning controls. There's rods that go all the way back through here, gearboxes, and as we walk around the back, you'll see how the plate tank circuit was tuned with what's called a variometer. Okay, so the variometer is where you have one turn that you can rotate in phase or anti-phase with the other part of the inductor. It's very clever. And as a matter of fact, just an interesting story, about 10 years ago when I was working at Harris with one of our RF engineers on a 250 kilowatt DX transmitter, another one of those digitally modulated transmitters, about a 250 kilowatt power block from which we built megawatt transmitters. We were experimenting with using a variometer to tune the output, so we didn't have to have these expensive vacuum variable capacitors in there. You could use a variometer. And one of the issues with the variometer was how much range can you get and change in inductance and so forth. We actually came out here, took one of these apart and measured it just to learn what you can do with one turn. We'll take a look at that when we go around back. Okay, any other questions about the power amplifiers so far? You'll have more when we go around back, but
do they have interlocks on these doors to keep you from going in?
Yes,
right?
yeah, there's interlocks. See? Yeah.
What was the tube life like? Any
No.
idea?
Do you know what the tube life was?
I don't know. I knew the price to retube the 20 tubes was $30,000 in 1935, $36.
I suspect that the tube life was not real good, and I'll tell you why. Every time, when they fired up this transmitter, it was like a NASA rocket launch. You had a crew of people, not one person. You didn't just go to a button and push a button. You had to bring this thing up in stages. And one of the stages was our friend Clyde Hanley, who's now no longer with us, but he's a young double E working here. He had welding goggles on, and before they brought up the high voltage, they would go in there and they'd look in the tube with these welding goggles to make sure that the filament was lit and aligned and wasn't shorted to the grid.
Wow.
So it was a big deal to bring this thing up. Okay.
How long has this transmitter operated this power? How many days?
1934, actually late 33, they began testing. It went on the air in May of 34 for regular service. It went for basically continuous operation until March of 39, and then was under an STA for experimental period operation only until 1943. In 1943, they were going to disassemble the transmitter, ship it to Australia, and use it as part of the war effort. Clyde Hanley, our friend, who just recently passed away about a year ago, Clyde was in charge of disassembling the transmitter, and here in the building is a log of what he did every day, logging his hours so he could get paid in the process.
Was it an economic reason why they shut it down, or was it regulatory?
It was regulatory.
Political regulatory.
There was a senator by the name of Wheeler from Montana whose relatives owned a small low-power AM station, who were bitching and complaining because the nation station was making megabucks off of advertising in 30 some odd states around the country. They were their own network. and these little stations were, just scraping along. So Wheeler attached an amendment to a bill, one guy, attached a, that
It's talking about how
we
Senator
should
Wheeler
only
from Montana
have a maximum.
kiboshed this whole thing in
The
1939.
bill got
His
passed,
family owned the radio
Crosley
station
protested
and
it.
didn't want the competition from
They
the
were only, by the way, they
nation's
were only
station.
granting them authorization for 6 months period
And
of time.
we
starting
got
in
he attached the rider to a bill.
So every 6 months they
They
had
got
to
it
renew
through Congress,
the
and that's what caused the
authorization.
FCC
And it became a
take it
battle
back
in the
to 50
Senate
kilowatts.
in
And it's been that way
38,
since.
late
Never been a
38.
AM station in the U.S. licensed
Some other
for greater than 50 kilowatts
And that put
since
him out
that
of business.
Wheeler bill.
And that kind of,
Yeah.
for Powell Crosley, that was
The
kind of
preservation
the
that we
the heart.
still have now,
You
is
know,
that just because everybody likes the history of it?
We don't know how long it's going to be here, but we've tried to archive. You look around here, you're going to see stacks of program logs and meter reading logs and things, and we tried to scan a lot of this stuff and preserve it, but we really don't know how long it's going to be here.
How about that old radio receiver too? That thing needs work.
They're prime
Okay,
coverage area.
so Jay, what I'd like to do is maybe take about 15 at a time.
Okay.
And we're going to, maybe you can lead them, or circumnavigate the transmitter.
Okay.
We're going to go up here and go behind and come back out the other side. But I'm going to stop by the tank circuit and describe it a couple of times to different groups, because you can't all see it at once.
So I can open up one of the bays.
Yeah. Can you guys know what a Faraday shield is? Sure.
Yeah.
Okay. This is the most perfect example of a Faraday shield. A Faraday shield is a sheet of conductive material. Doesn't necessarily have to be a solid sheet. It could be a lot of little rods that are closely spaced, like we're looking at there. And it's a sheet of material that can be put between two inductors that will eliminate any electrostatic coupling or electric field coupling between those inductors. But if it's only grounded on one side, one edge, it will not affect the magnetic field. So what this is a Faraday shield, this thing. You notice this is insulated material here. It is grounded at the top to the cabinet. And what it does is it eliminates capacitive coupling between the primary tank circuit inductor, and this is the output coupling circuit here. Why do they want to do that? Harmonic suppression. Try to keep the higher frequency harmonics from coupling through. So this is, as I said, this is the most perfect example of a Faraday shield I've ever seen. Now, the tank circuit here, let me step over here and see if I can reach this. Maybe I can turn this. There is a single turn loop. This one's parked in an odd position, but there's a single turn loop back there that rotates 180 degrees. So it goes from this position to that position, back on that first inductor. And that is changing the inductance enough to tune it right to resonance. You can see that very clearly here, the bread racks, as we call them. Those are the parallel plate air capacitors that resonate the push-pull tubes on this pancake inductor. This inductor here is the output coupling inductor, and it moves. There's a jack screw here. If somebody were to go around front and turn it, you would see this thing move in or out. So this, as it moves in, it increases the coupling. So this is your, think of this as a loading control on your Pi network. The tuning control is that half turn on this inside inductor, and this is the output loading control. Okay. Now this piece broke off here. It's supposed to be soldered there, but anyway. So this is where the output is coupled from this output coupling loop. It goes down into this matrix where there's a switching matrix down there that can put all of these in series. All
How much
three
current are we talking about at this point in time, Geoff?
I don't know off the top of my head.
Make a wag.
Well, let's just take a guess. 100 ohms, and 180 to 200 kilowatts in the 100 ohms. So do the math.
Yeah. It just seems funny with everything else is so huge, and then it's like what, 3/4 inch copper pipe. So.
Yeah, I would guess the current here is maybe 50 amps or something like that.
Certainly
Yes,
well
I
within
have
the
a
range of
calculator.
that conductor. But
Yeah, but that's certainly within the range of this kind of a conductor. Okay.
Was there water inside
No.
the conductors? Or
No.
Okay,
No,
just
it's not-
tubing.
Just a hollow tube.
Not water cooled.
Hollow
See
tube.
all these little Corona things on here. That's what these are for, because there's high voltage on these points. They didn't want Corona coming off, and that's what that's for. Treat it so those knobs that you saw on the front down where the Pyrex pipes are, one of those is it cranks this thing in and out, and the other one rotates this loop. You can see right here's the piece that rotates. And there you can see the gearbox right there. Okay. I'll take you guys down this way and then I'll get back to the next group. Here is another where you can see the loop a little bit there. Take a look at the construction here. I mean, these are wooden doors, guys. You know?
Wooden doors.
Wooden doors, but they're covered with copper sheeting.
You know any fires? All this power?
No, it never burned out. Okay, you guys should. I mean, it's sad. Yeah, all this stuff. The DOA has an archive this is going to come and work out. So just find your way back out around there, and I'll go through the next group.
Oh man, it was good. I had the Sony receiver, this AM stereo.
The little portable radio? I always wanted one of those.
And also Chrysler back in the early 90s had I guess it was a con system.
Okay, guys, around and back into the back room, if you would, please.
Now this is a modulation transformer. This is an audio transformer. 30 to 10,000 of the cycle. Frequency response. It got all out of here a long time ago. I never saw it.
The other one?
Yeah, it sat right here. Then you'll see a picture of Pal Crosley standing here between the two. It's around there. Okay, so yes, this is an air dielectric capacitor.
Air dielectric capacitor.
It's part of an harmonic filter.
Oops, sorry.
So instead of a vacuum variable, these are cylindrical aluminum and with a coaxial. It's really just like a piece of coaxial transmission line, but it's a capacitor.
Piston cap, basically.
Yeah.
Geoff, a couple of facts that just came out of an article that we discovered.
Okay.
The filter capacitor for the DC supply was 270 microfarads, rated to the fact that it was a 12,000 volt supply.
Right.
The audio coupling from the series modulation transformers, they didn't run DC through it, 500 microfarads, rated at something over 24 kilovolts.
Yeah, so you saw that modulation reactor out back. That's an inductor that has high reactance and audio frequencies. That's where the DC feeds to the power amplifiers went. But these transformers were AC coupled through this large capacitor that Jay just talked about. They didn't want to put DC current in the winding of the transformer because that would affect the audio frequency response of the transformer. So it's pretty much the same as what you see in a Hamburg today. Usually you don't put the plate current through the modulation transformer. You have a separate reactor for that. Now you can see some vestige of the switching arrangement up here. The amplifiers are right above us here, and those holes in the floor where the output conductors come went into these sections here. I don't know exactly how the switching was done. There was some kind of a sliding arrangement that engaged or disengaged the inductors, but the switching arrangement was here, and this is the output line right here. That piece of aluminum line, it's got a piece of heliax just laid out there, but that was the line that carried 500 kW. Not that big.
No.
You know, it's only about 8 inches in diameter or so, but
No standing waves.
yeah. And it was high impedance. It was 100 ohms.
100 ohms.
Yeah. Over where these backup generators are is where all those motor generators were from Coleman's when they were running the 1 DC.
Probably pretty noisy down here.
Yeah, well, it could get very noisy if those crank up right now. Okay, this is the harmonic filter over here.
Oh, the harmonic filter.
So it's got a big array of mica capacitors, series parallel mica capacitors, and a big inductor.
Thank you.
I think this filter was originally out at the base of the antenna.
This? No, it was here.
Here?
This was the actual changeover also, between the 50 and the 500.
Okay.
Yeah.
Okay.
But the tuning unit was out of the building.
So how far could you hear the second harmonic from the maybe with all the filtering on 1400 kilohertz?
I have no idea.
Well, there was no station assigned to 1400 in Cincinnati.
Take EV off of 500 kilowatts. It's
Yeah.
still a pretty good signal.
Yeah, you still can get a second harmonic a little bit.
So when you depart through here, Ted has graciously given us a QSL card.
Oh wow, thank you, thank you.
Station.
QSL card for everybody.
Hey, thank you.
Thank you.